Hi everyone, welcome back to our discussions of the History of Astronomy unit. In the last set of our discussions, we're going to discuss Newton's laws of motion. This is essentially the culmination of the history of astronomy that we've been discussing so far into what we could think of as what gives rise to most of what we do in modern astrophysics outside of applications that require special relativity or general relativity or quantum mechanics. So, if you're following along in the OpenStax textbook, this goes along with sections 3.2 through 3.6. I think through 3.6, but the end of chapter 3 of the 2017 edition of this book. So first, just kind of some warm-up items, some common misconceptions. So one is that astronauts are weightless because there's no gravity in space. Another is that spacecraft must keep firing an engine in order to keep moving. Another is that rockets accelerate by pushing against the air. And another is that rockets must reach the escape velocity to get into orbit. These are all misconceptions that we are going to address in the rest of this unit. So first of all, getting a concept in mind, the acceleration due to gravity. This is the rate at which a falling object will change its velocity. And by falling, I mean it could be a projectile, or it could just be something that is dropped and falling vertically, or it could be something that is thrown upward and then allowed to turn around and fall vertically, etc. In any case, it's always going to increase its downward velocity by 9.8 meters per second if it's near Earth's surface. So we say that it accelerates downward at 9.8 meters per second, or in using the contracted form of that, 9.8 meters per square second. So what that means is that if you drop an object or allow an object to fall, whatever, every second its downward velocity increases by 9.8 meters per second. So if it was going upward at 29.8 meters per second at one instant, well, 1 second later, its upward velocity would be down to 20 meters per second. And another second after that, it would be down to 10.2 meters per second. Another second after that, it would be down to 0.4 meters per second. In other words, it would have reached pretty close to its maximum height, because another second after that, it would be actually moving downward at a rate of 9.4 meters per second. That is 0.4 minus 9.8, etc. You get the picture. So that's what we mean by acceleration. It's the rate at which its velocity is changing. In this case, the acceleration is caused by the gravitational field of Earth. So we say that the acceleration due to gravity near Earth's surface is 9.8 meters per square second. That's often symbolized by the lowercase letter g, so just something to keep in mind. Now, what was realized around the time of Galileo, and in particular by Galileo, is that objects will fall at the same rate regardless of their composition, if you ignore things like air resistance. In fact, anytime there is a gravitational field, objects are going to have weight and they are going to fall. Now, I should mention something about gravity. Gravity is a special force in that it's not really a real force in the traditional sense of the term force. Yes, we include it in free body diagrams because high school physics teachers like us to do that, and first-year college physics teachers like us to do that. But I mean, gravity, it's kind of weird. I mean, you can't actually feel gravity. And the reason you can't feel gravity is because it's not a real force. But we pretend that it's a real force because of the fact that what we're always actually feeling is the normal force, unless we're actually falling in the air. And when you feel the normal force, you're feeling this normal force because your natural tendency is to fall. So because of that, we pretend that gravity is a force, and we mark it on free body diagrams and stuff like that. But in any case, when you're not being upheld by the normal force, you are falling. Well, when you are falling, that has the same experience as being weightless. You feel weightless when you are falling, if there aren't any other forces acting on you. And that's really the essence of the fact that gravity isn't really a real force. You feel the same whether you're falling or whether you're actually deep in space not moving at all. Either way, you feel weightless. So yeah, astronauts feel weightless because they are falling along with the spacecraft as they are orbiting around Earth. So, same thing would happen if you were in an elevator and the cable suddenly snapped. You would feel weightless. And what that would mean is that a scale would read 0, because scales measure normal force, so you wouldn't feel anything. If the elevator is accelerating downward, in other words, it's getting faster in the downward direction or getting slower in the upward direction, the scale is going to read a value less than your weight. And the extreme value of that is if the cable snaps, or if it simply allows you to fall at 9.8 meters per square second for a short period of time. If the elevator is accelerating upward, that is, if it's speeding up in the upward direction or slowing down in the downward direction, it's the same thing, the scale will read a value that is larger than your weight, because the scale will need to exert more normal force than your weight in order to cause you to accelerate upward. This is the essence of something called Newton's second law that we're going to get to soon. And similarly, if you're moving at constant velocity, or if you're at rest, the scale is just going to read whatever your weight is. You can experience weightlessness by getting in this vomit comet, which the people tell me that this plane is a C-135, if I remember right, or a KC-135, something like that. But in any case, they accelerate upward, and once they get high enough and they're moving still in a bit of an upward trajectory, they cut off the engines and just allow the airplane to be a projectile. And as that happens, the passengers feel weightless, and you can perform physics experiments that require zero gravity. And in fact, we're going to talk about some of those later in the course. Now, what about escape velocity? This misconception about needing to reach escape velocity to go into orbit. So, a thought experiment that is attributed to Sir Isaac Newton, he at least mentioned it in his famous work, the Principia, is that if you fire a cannon from the top of, say, the tallest mountain on Earth, and just fire it parallel to the ground, then, of course, it'll land very far away. But if you fire it with greater and greater energy, then after a while, by the time it falls, it will have traveled a significant distance, and it will have to fall a bit more in order to account for Earth's curvature. And if you fire it fast enough, then the rate at which it's falling is going to be the same as the rate of Earth's curvature as it travels. Once that is achieved, that is orbital velocity. Spacecraft, in order to go into orbit around Earth, reach orbital velocity. Spacecraft, in order to never return, need to reach escape velocity, or in order to, quote, escape from Earth's gravitational field. What we mean by escape from Earth's gravitational field is that if you were to allow it to go forever, it simply wouldn't come back. In other words, spacecraft going into orbit reach orbital velocity. If they reached escape velocity, they wouldn't go into orbit because they wouldn't come back. Now, Newton's Principia is something that I just referenced. In 1687, he published his magnum opus, his what some people consider to be the greatest work of physics in history. In fact, some even say it's the greatest work of science in history. And among many, many other things, he published his 3 laws of motion. The first is that objects maintain constant velocity unless acted upon by an unbalanced force. Notice that by constant velocity we mean constant speed and constant direction. Now, the whole point of this is to help to overturn ideas of ancient philosophers like Aristotle, who thought that objects naturally came to a rest and required a force to prevent that from happening. Newton's first law notes that the natural state of being for any object is to maintain constant velocity. That's it. It maintains constant velocity. The only reason it wouldn't maintain constant velocity is if there's something that's not so what one could call natural acting on it, something that we would call a force. If it's interacting with something, then there could potentially be an unbalanced force. By unbalanced, we mean that if there is more than one force acting, they don't cancel each other out. So for example, right now, while I am recording this video, I'm sitting in a chair. The force of gravity downward on me is canceled out by the force of the normal force from the chair upward. So, since those forces cancel, they are balanced, and thus I maintain constant velocity, which fortunately is zero, at least in the Earth surface reference frame. Newton's second law is that an object's acceleration is equal to the force acting upon it divided by the object's mass. So in other words, let's say we have a situation where Newton's first law isn't relevant. In other words, an object isn't maintaining constant velocity. Well, that means there must be a force acting on it. Well, how much force is acting on it? We can figure that out by measuring the object's acceleration and multiplying by the object's mass. Now we know how much force is acting on the object, at least what the net force is acting on the object. When we say F equals ma, force equals mass times acceleration, we really mean the net force acting on the object. So F is force, m is mass, a is acceleration. Newton's third law is that for every force there's an equal and opposite force. This is actually a direct implication of Newton's second law combined with the conservation of momentum, that the total momentum before an interaction is equal to the total momentum after an interaction. We'll have more to say about momentum in a little bit. More on Newton's first law. Galileo was quite familiar with this. It's also called Galileo's law of inertia. Even people before Galileo, like Niccolò Oresme, I think around 1360, realized that if an object is at constant velocity, there's no way of doing any experiment that could distinguish between whether it's that object that's moving or whether it's everything else that's moving in the opposite direction. In other words, there's no such thing as absolute rest. In fact, this whole concept that we often call Newton's first law was taken even further into something called Einstein's first postulate of relativity, something that we'll talk about later in the course. So, in the actual class, I showed a number of videos involving Newton's first law, demonstrations of Newton's first law, where, like let's say a person is in a boat that is moving very fast on a lake and suddenly the boat swerves. Well, the person's going to go flying out because the natural state of being for the person is to maintain constant velocity. So if the boat makes a sudden turn and the person isn't strapped into the boat, then the person will just keep going at whatever the boat's velocity had been. Similarly, if you're in a car going at constant velocity and you suddenly skid to a stop, you feel a force pulling you forward. There is no real force pulling you forward. What you're actually feeling is the seatbelt holding you back. Because your natural state of being is to keep going forward at that speed. Similarly, if you're driving on an icy road, the car's natural state of being is to keep going straight at the same speed. So that's why it's very dangerous to drive fast around curves, especially if the road is slippery, because your natural state of motion is to keep going in a straight line at the previous speed. So trying to go around a curve where there isn't much friction between the tires and the road, say a snowy or icy road, well, you better be going very slowly so that there can be enough friction. We'll have more to say about that later. So misconception number 2, spacecraft need to keep firing an engine to keep moving. Well, Newton's first law says that the natural state of motion for objects is to maintain constant velocity. And as such, we have a number of spacecraft like the Voyager 1 spacecraft, Voyager 2 spacecraft, the Pioneer vehicles, the New Horizons spacecraft. Those are all on their way out of the solar system. They have reached escape velocity, and they don't need to keep firing an engine to keep going. In fact, after leaving Earth, only rarely did these spacecraft fire engines, and in those cases it was to redirect their motion or to help to achieve gravity assists from planets, which we'll discuss very soon. Now, Newton's second law, force equals mass times acceleration. The point is that there is something that resists changes in motion. That something is given by the general name inertia. Now, if we're talking about a resistance to a change in translational motion, the term that we use for inertia is called mass. So the larger an object's mass, the larger the force you need to exert in order to give it the same acceleration. The smaller the mass for a given force, the larger the acceleration is going to be. The units of force are called newtons. People found that they were performing this F equals ma calculation so often and getting units of, let's say, mass units are kilograms, acceleration units are meters per square second. So the units for force would be kilograms times meters per square second. Well, every time they would have to write those units at the end of their answers so that their physics teachers wouldn't count off 1,000,000 points. So eventually people said, okay, we need to give a name to these units so that we don't just have to keep writing this cumbersome kg.m over s power 2. So we're going to call that a newton, after Isaac Newton. So a force of 1 newton will accelerate a 1 kilogram mass at a rate of 1 meter per square second. That's the definition of the newton. So the idea is you apply a net force to an object. That object is going to accelerate at a rate given by the net force divided by the object's mass. Also notice that the direction of the acceleration is the same as the direction of the net force. Newton's second law is a vector equation. Now we mentioned that objects that are changing direction are also accelerating, because after all, velocity is speed and direction. And so if something's changing direction, that must be accelerating, and therefore a force on it must be acting. Well, if something's going in a circle, that means it's constantly changing direction. In fact, uniform circular motion is a very important unit in physics to understand very well. We're not going to get into it in a whole lot of detail in this class, because this is not an astrophysics class. But I do want to mention that when an object is undergoing uniform circular motion, that is constant speed at a constant radial value, then the acceleration that the object is experiencing is given by the equation v squared over r, where v is the speed and r is the radius of the circular motion. We call this centripetal acceleration. Centripetal means center seeking. And since the direction of the force must be the same as the direction of the acceleration, the direction of the force is toward the center of the circle. So that's important to keep in mind. If you're swinging an object that's attached to a string around your head, you can feel yourself having to exert a force on the string. That force is coming from your hand, and that ends up going into the tension in the string, but the overall net force is toward the center of the circle. If you get rid of the net force, the object is going to go flying at constant velocity in accordance with Newton's first law. So, for example, the string breaks, and the object will continue on at constant velocity. Now, Newton's third law. Every force results in an equal and opposite force. If you are jumping off of a skateboard, you will exert a force backward on the skateboard in hopes that the skateboard will exert a force forward on you. Of course, the force forward on you is going to be the same as the force backward on the skateboard, because that's what Newton's third law tells us. And the result of this is that the skateboard will accelerate at a much higher rate, because the skateboard, hopefully, is a lot less massive than you are, going back to Newton's second law. So, misconception number 3. Rockets accelerate by pushing against the launch pad or against the air. That's not true. They also don't accelerate by pushing against the ground. Instead, they accelerate by pushing against spent rocket fuel, which goes out the exhaust. So the explosive action of the burning of the rocket fuel exerts a force on the spent rocket fuel in one direction, but Newton's third law, therefore, that spent rocket fuel is exerting a force back on the rocket, causing the rocket to rise, or to go in whatever direction it needs to travel. Now, Newton's law of universal gravitation. This is not so much one of his laws of motion, but more a law of the fact that whenever there's an object that has mass, it's going to exert a gravitational force on anything else that has mass. The whole essence of the law of universal gravitation is that the force of gravity between two massive objects is first proportional to the product of the masses, and second is inversely proportional to the square of the separation distance between the centers of the objects. And that proportionality constant, known as big G, or Newton's gravitational constant, is about 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And generally speaking, it is considered bad form to italicize units because it's actually the physical quantities or the constants that are supposed to be italicized, but the units are not supposed to be. So I'm going to do this little PowerPoint trick of fix it, and it's fixed. So here's how the equation often looks. Usually we use the symbol R for the distance from the center of, or the centers of the two objects. It's what we call a radial coordinate. And a lot of times it's lowercase r. Here we call it capital R, but it really doesn't matter. But again, it's a 1 over distance squared force law. If you double the distance between two massive objects, then the force of gravity is going to be 1/4 as strong. If you multiply the distance by 5, it's going to be 1/25 as strong. So for example, two asteroids floating in space. One has a mass of 1 trillion kilograms, the other has a mass of 5 trillion kilograms. These are like masses of mountains. So what if the force of attraction between them is 10 newtons? How far apart are their centers of mass? So I write my givens, and here I used an old format for the equation where it didn't allow me to non-italicize the units, and I didn't feel like going back and redoing the whole problem and changing the format so that I could non-italicize the units, so I just left it for the video. But anyway, we write our givens, we have our equation, and we plug the numbers in. It's usually better form actually to manipulate the equation in terms of the variable you're trying to solve for first. So I would kind of go back here and multiply both sides by r squared, divide both sides by f, and then take a square root, and then plug in my numbers. Either way, I'm going to get a distance of 3.3 times 10 to the 13 meters squared for my distance squared. Don't forget to take a square root of that. And then you get 5.78 times 10 to the 6 meters for that distance. That's a little smaller than the radius of Earth. It's like 90% of the radius of Earth. But still, 10 newtons is a measurable force. I mean, that's about the force that a 1 kilogram object would have if it's in your hand. So that's the force between these two mountain-sized asteroids, even if they're as far away from each other as about the radius of Earth. So again, Newton's law of universal gravitation tells us that anything that has mass is going to exert a gravitational force on anything else that has mass, and that force extends infinitely far. So in space there's still gravity, and in this case the astronauts are actually close to Earth's surface. They're close enough that their actual true weight is about 91% of what their weight would be on the surface of Earth. It's just they feel weightless because they're falling. So, and that 91% bit we get by taking the ratio of their distance from the center of Earth when they're in orbit, comparing with the radius of Earth, squaring it, because it's a 1 over r squared force law, and then inverting it, because it's in the denominator. And when you do that, you get 0.91. So, their true weight at the distance of their orbit is 91% of what it is on the surface of Earth. Now, with Newton's law of universal gravitation, this allows us to compare. It's like, well, wait a second. We know that the force of gravity is big G times m1 times m2 over distance squared. But let's consider a circular orbit. Well, I know the force required to cause something to go in a circle. Remember that formula for centripetal acceleration, v squared over r? We'll multiply by the mass of the thing that's going in the circle. We'll call that m2. And you get m2 times v squared over r. Well, that must be equal to Newton's law of universal gravitation. So that mass is going to end up canceling. And I have an equation for now the speed of an object in a circular orbit. And I could manipulate that and plug in the fact that the speed of something going in a circle is given by 2 pi times the radius of the orbit divided by the period. And lo and behold, after a little bit of mathematical rearrangement, get this equation. We see that the square of the orbital period is proportional to the cube of the radius of the orbit, which here I've called A because it's actually the semi-major axis of the orbit using the correct term. And this is actually the result of Isaac Newton's derivation, not the result of the hand-waving derivation that I just gave. When Isaac Newton derived this, he assumed that the two masses are not necessarily negligible, and as a result, Newton's third law, the force of gravity of one object on object 2 is equal to the force of object 2 on object 1. Both objects are actually going to orbit around their common center of mass. So Newton took all of that into consideration and also considered the possibility of an elliptical orbit and obtained this relation. In other words, usually the way we write this is period squared equals 4 pi squared a cubed over gm, where m is the total mass. In other words, the mass of the two objects combined. So this allows us to make some interesting calculations. Well, consider the International Space Station orbiting around Earth. So it takes it about 92 minutes to go around once at an orbital radius of 6,750 kilometers. That is 372 kilometers above the surface, making it that far from the center of Earth. So with that in mind, we can plug these numbers into the equation. In this case, I kind of canceled my units ahead of time and recognized I was going to get kilograms on the outside. But there's that orbital radius. That would be the orbital radius in meters, which I canceled the meters, which come from 3 factors of meters from big G right here. And the orbital period, this is what 92 minutes translates into in seconds. So the seconds squared also cancels with some seconds squareds in the big G, and what's going to be left over are kilograms. So from that, we deduce that the mass, well, technically the mass of the system is 5.97 times 10 to the 24th kilograms. But the mass of the International Space Station is only about 100,000 kilograms. So very small in comparison to the mass of the system. So basically, all of that mass is the mass of Earth. So just by watching something in orbit around Earth, we get the mass of Earth. We also get something close to that just by watching the moon. So consider the moon. It takes our moon a little over 27 days to go around once. So that's this many seconds, 2.36 times 10 to the 6th seconds. And the average radius of our moon's orbit, the semi-major axis, is about 384,400 kilometers, or 3.844 times 10 to the 8 meters. So with that, we can plug into our equation. So there's our equation, first stated in the way it's typically stated, and then I solved for the mass of the system, multiplied both sides by the mass of the system, divided both sides by t squared. And then, don't forget about our givens, which were on the previous page. Well, now we plug them in. Notice the meters cubed cancels, the seconds squared cancels, and what's left over, 1 over kilograms is kilograms. So there's the mass of the Earth-Moon system. Oh, it's a little bit more than the mass of Earth. Well, that's because even though our moon's mass is a lot less massive than Earth's, it's not completely negligible. It's about 1/80th of Earth's mass. In fact, if we were to perform a more precise calculation and compare the answer that we got with this with the answer that we got for the space station example and subtract the two numbers, that would be the mass of the moon. Pretty cool, huh? Watching objects orbiting is how astronomers figure out the masses of objects. That's how you can figure out the mass of a planet. That's how we know the masses of all of the planets in the solar system. In the case of Mercury and Venus, which have no moons, we've had spacecraft encountering those planets or in orbit around those planets. Even all of the officially named dwarf planets, except for the asteroid Ceres, have moons around them. So based on the motions of those moons, we can deduce the masses of those dwarf planets. Even the asteroid Ceres has had the Dawn spacecraft in orbit around it, so based on that orbit, we know the mass of Ceres real well. Now, anything that has mass will, in the presence of a non-negligible gravitational field, also have weight. The value of an object's weight is equal to its mass times the acceleration due to gravity at that location. But, depending on where the object is, the weight can be different. The acceleration due to gravity at Earth's surface is about 9.80 meters per square second. At least after you take into account the spinning motion of Earth and stuff like that. However, on the surface of the Moon, it's about 1.6 meters per square second. On the surfaces of Mars and Mercury, it's about 3.7 meters per square second. That means that objects will have different weights, depending on whether on the surface of Earth, Moon, Mars, Mercury, or somewhere else. However, their mass is the same regardless. The mass, remember, is a measure of the resistance to an object's change in its motion. So in other words, it is just as difficult to throw a big smelly old troll on our moon as it is to throw it on Earth. However, because of the fact that he weighs less on the moon, it's going to be a lot easier to lift the troll on our moon. In fact, it'll be 6 times easier because his weight is 1/6 of what it is on Earth. That doesn't mean that you'll be able to lift him quickly because, after all, he has a big mass, so lifting him quickly would require accelerating him quickly. But you would still find it easier to lift such a troll on the surface of our moon. Now, what about orbits? So, we've talked about the fact that an object in orbit is constantly changing its velocity, and that means that it's accelerating, and that acceleration is controlled by Newton's Law of Universal Gravitation. Now, if you're trying to get something into orbit, you can take into account the fact that Earth is spinning. So, people sometimes think that rockets launch straight up. They don't completely launch straight up. They initially launch straight up just to get off of the launch pad and then to get above a decent amount of Earth's atmosphere. But once they do that, they roll over and start to travel horizontally, as you can see in this picture of a space shuttle launch from Cape Canaveral. Which way is it actually traveling at this point? In this case, it's going toward the east because Earth is rotating from west to east. So it's taking advantage of Earth's rotation so that it can use some of that speed in order to attain orbital velocity. Now, the speed of orbital velocity can be found by, as I mentioned before, combining Newton's Law of Universal Gravitation, big G, big M, little m over r squared, with the equation for centripetal force, little m times v squared over r. Well, the little m's are going to cancel. One factor of r is going to cancel, so you're left with v squared equals big G times big M over r. Or, well, I called it little r, but just r. And solve for the speed, take the square root. So that's the equation for the orbital velocity of an object. So you plug in the mass of the thing being orbited, you plug in the radius of the orbit, that tells you how fast you're going to need to go in order to have the object in orbit. So in the case of Earth, that orbital velocity is a little less than 8 kilometers per second, or about 17,700 miles per hour. Surprise, surprise, that's the speed at which the space shuttle would travel when it was in commission, and it's about the speed that the International Space Station is traveling. Now, geosynchronous satellites travel a lot slower than that because they need to stay above the same point on Earth, so they're going to be orbiting much farther out, where, in other words, where r is bigger, so the orbital speed is going to be less. Now, escape velocity. The formula for escape velocity can be derived from conservation of energy, but long story short, it's equal to the orbital velocity times the square root of 2. So in order to escape from Earth, something needs to travel at 11.2 kilometers per second. If I throw a baseball at 11.2 kilometers per second, it's never going to come back. It still feels Earth's gravity, in other words, it's going to slow down, but as it slows down, it's also getting farther and farther, so the rate at which it's going to slow down is going to become less and less, and the escape velocity is the speed at which the rate at which it's slowing down is exactly equaled out by the fact that it's getting farther away and thus feels a smaller force of gravity. So, of course, it's larger than the orbital velocity by, again, a factor of square root of 2. Quick example. Calculate the escape velocity from our solar system for a satellite located in Earth's orbit, given our Sun's mass. So here you have the mass of the Sun and the radius of the current orbit, or at least the distance it is from the center of the thing causing the gravitational field. There's our formula for escape velocity. Now you plug in the numbers, and upon evaluation, you find that that speed is 4.2 times 10 to the 4 meters per second. That's like 90,000 miles per hour. And I'm sorry, but no spacecraft has ever achieved that speed. But wait a second. Didn't we just talk about how a number of spacecraft are escaping from our solar system? Like the Pioneers, the Voyagers, New Horizons? Well, that's because, one, they're a lot farther away than this radial value of Earth's orbit. But, I mean, how did they get that far away in the first place? They achieved that speed, or at least a sufficient escape speed, by gravitational assists. So let me show you how that works. Here, using the PhET My Solar System simulation, we have a satellite, which is in green, being affected by two planets, which are purple and blue, and it's also in orbit around the Sun. So here we go. There's the satellite. So it got a gravitational assist from the purple planet, and then again from the blue planet, and now it's escaping from the system. Now, notice that in so doing, it stole some energy from these planets, and as you can see, those planets are now in different orbits. Let me reset this and show it again. So notice right here, it's just behind the purple planet. It's just behind the purple planet, and because it's just behind the purple planet, that means it's being pulled forward. It's being pulled forward in the direction of the purple planet, but that's perfect for the green because that will also give it some extra forward velocity. It's actually stealing energy from the purple planet's orbit. A very negligible amount of energy because the mass of the green satellite is much smaller than the mass of the purple planet. So now it's going faster and thus has a bigger orbit, as you can see. So start again. And now it's behind the blue planet. And as the blue planet goes ahead, it's pulling the green planet from behind. Well, it's giving a pull to the green planet. The green planet is behind the blue, or sorry, the green satellite is behind the blue planet. And this time, it ends up giving it enough energy that it ends up escaping from the system. It's not going to come back. So this is what we call a gravitational slingshot. So again, when objects reach escape velocity, they don't come back. They escape from the system. So now we need to turn our attention to some other concepts that are relevant in our discussion of physics and astronomy and how these relate to each other, and particularly concepts that will be important for us for the rest of the course. In particular, we will discuss momentum and conservation of momentum, and in particular angular momentum and conservation of angular momentum, as well as conservation of energy and some other relevant physics that we will need for the rest of the course. And we will look at that in our next video. Hope to see you all then, and thank you for watching.